Cadillac Service Department presents a roundtable program on the latest word in year-round comfort. The inside story about automatic temperature and humidity control, regardless of season, called Weather Forecast. Featuring Comfort Control, an exclusive Cadillac option. The industry's first heater air conditioner system capable of sensing changes in the outside weather conditions and compensating for them automatically to maintain a controlled temperature inside the car without any need to reset the dial. Comfort Control will be found on all air-conditioned Series 62 and DeVille cars and on the Fleetwood 60 Special and Eldorado, while air-conditioned Fleetwood 75 sedans and commercial chassis use the dual heater air conditioner system having the same controls as in 1963. Comfort Control utilizes new sensing and control devices added to the combination heater air conditioner to make the system operate automatically. In this cutaway diagram, we can see that the air mix principle of operation continues practically unchanged. In winter, cold outside air is drawn in by the blower and directed through the evaporator. Most of the air then flows through the heater. If any cold air is called for, it blends in with the heated air entering the heater duct. In summer, the outside air is warm and humid, so the air conditioner system operates to chill the evaporator. This not only cools the incoming air, but also removes a lot of moisture. The cool air then flows directly into the air conditioner duct, while the temperature door blends in a little heated air when needed. To make the evaporator cold, all the other underhood components of the air conditioner system are still used, of course, including the compressor, condenser, and so on. What we've learned in the past from such roundtable films as Warm Up for Spraying and Blend for Comfort still holds true, both in theory and in service procedures for the heater and air conditioner. But to what we already know, we have to add some additional understanding and information to go along with the additional convenience of Comfort Control. An understanding, for one thing, of exactly how the system operates when the temperature dial is rotated, when the sliding lever is moved, and when the car is started after being parked in various kinds of weather. To know what to expect of the system means we have to learn about the new components in the Comfort Control, the sensors, the transistorized amplifier, the transducer, the power servo, and the control panel itself. A lot of fancy-sounding names, possibly, but nothing really difficult to understand. For example, the sensors are really the thermometers of the system. There are 3 of them. One for the outside air as it enters, one for the heated or cooled air coming out of the ducts, and one to check the in-car temperature of the air in front of the driver. All 3 sensors employ a small, disc-shaped, temperature-sensitive resistor that differs from ordinary metals, having high resistance when cold and low resistance when hot. 2 of the 3 sensors incorporate bypass resistors, which reduce the sensitivity for calibration purposes. The in-car sensor is the one without a bypass resistor, so it can act full strength. This is the most important one, of course, and it's the final authority on car interior temperature. The outside air sensor is the primary weather forecaster of the system. It's located in the air inlet duct, where it can check all incoming fresh air and alert the system as to whether heating or cooling will be required. The duct sensor is located inside a crossover tube between the heater duct and the air conditioner duct. This sensor checks the air being discharged into the car to help stabilize the output temperature. Since its crossover tube is open to both ducts, this sensor can sample the air, regardless of whether the system is functioning as a heater or as an air conditioner. Or we might say whether the system is operating in heater mode or air conditioner mode, some new terminology that better describes the automatic operation. And to go along with this, the diverter valve has been renamed the mode door. It still performs the same function of directing the air either to the air conditioner duct, as shown here, or to the heater duct. The mode door is operated by a vacuum diaphragm and always moves to one position or the other, never in between. Next to it, the temperature door works differently. It may be positioned at any point between one extreme and the other to vary the blend of heated and cooled air. This variable position is controlled by a mechanical link from the muscle man of the comfort control system, the power servo. Although vacuum operated, this unit can assume any number of positions because it is supplied with a regulated vacuum. But moving the temperature door isn't the only job the power servo performs. The power servo assembly also includes a rotary vacuum valve to operate the mode door and other vacuum control units, and a blower speed switch to control the blower speed automatically, in addition to operating the temperature door link. The power servo handles these three jobs according to a carefully prearranged program that represents the ideal way to operate the combined heater-air conditioner, constantly making the best possible decisions as to the proper mode, the minimum blower speed, and the precise temperature setting needed. The power servo doesn't make these decisions by itself. They're built in. It gets its instructions in the form of a regulated vacuum, as we said. A strong vacuum means make it warmer, while a weak vacuum means make it cooler. These instructions are, of course, based on the weather reports from the three sensors. This information originates as an electrical voltage developed by sending battery current through all three sensors connected in series. This current always flows whenever the engine is running. The circuit is completed by going through a fixed resistor and the temperature dial rheostat to ground. With the generator charging the battery at about 14 volts, there will be approximately 13 volts left over after going through the sensors. This will vary when the sensors change temperature or when the dial is moved. The amount of variation may be only a few tenths of a volt, but this is all we need to control the entire system. In the control panel, along with the rheostat, is a transistorized amplifier. This amplifier magnifies the small voltage variations caused by changes in temperature. Even a change as small as a tenth of a volt can be built up enough to shift the system all the way from heating to cooling. This voltage is fed into the amplifier, where any variations are built up into a variable amplifier output that may range all the way from 0 volts in cold weather up to 9 volts in hot weather. So far, so good. But we're still dealing with voltage, while the power servo responds only to vacuum. Obviously, these two units can only communicate through an interpreter, and that's the function of the transducer, to interpret the voltage from the amplifier and translate this into a regulated vacuum to the power servo. The higher the voltage, the more the transducer tends to shut off the vacuum supply. The amplifier voltage is fed into the transducer, which is supplied with full manifold vacuum, but regulates the vacuum passed along to the power servo. The lower section of the transducer contains a thin special alloy wire which pulls down on the vacuum regulator valve at the upper end. The amplifier voltage goes through this stretched wire and heats it, causing it to relax some of its tension. Inside the vacuum regulator, there is a vacuum port and an atmospheric port, and regulated vacuum originates in the chamber between them. When the wire is tight, it pulls on the diaphragm and releases a stronger vacuum to the power servo. The diaphragm is balanced between air pressure and the pull on the wire. When the voltage is low, the wire tightens up, producing a strong vacuum. When the voltage is high, the wire relaxes, producing a weak vacuum. And that's how the message gets through from the sensors to the servo. If it's too warm, a high voltage causes a weak vacuum, making it cooler. If it's too cool, a low voltage causes a strong vacuum, making it warmer. With this ingenious control system standing guard, any temperature changes are counteracted as soon as they occur, and the temperature is stabilized within 1 degree. The complete control circuit diagram includes the items we've been talking about, plus the electrical power supply. It also includes a vacuum reserve tank for the transducer and power servo. The temperature door, you'll recall, is connected by a mechanical link to the power servo. Now, as for the air mix system, here's the power servo back in its natural surroundings, operating the temperature door to direct traffic in the air duct assembly. When the car is first started on a cold morning, as soon as the engine warms up a little, the comfort control system starts in the maximum heating condition. Only outside air is taken in, and the blower runs at full speed to warm up the car as quickly as possible. All the air comes through the evaporator and circulates through the heater core on its way to the heater ducts. In summer, the system starts right away in maximum cooling to cool off the car as quickly as possible. Again, the blower runs at full speed, but this time it takes in mostly recirculated air. This air is forced through the cold evaporator, goes by the temperature door, and into the air conditioner duct. In mild weather, the system will soon settle down to regulating, with the temperature door nearly centralized. The blower has slowed down, and it takes in only outside air. The mode door can be set either for heating or for cooling. When it's warmer than 35 degrees outside, the compressor clutch will be switched on by the thermostatic compressor switch mounted in the air inlet assembly together with the outside sensor. This sensor checks the incoming air and forecasts whether heating or cooling will be required. Then, when this air passes through the system, the duct sensor checks it again. This reading will be just the opposite, because the air has been warmed or cooled in the meantime. These two sensors nearly always offset each other. In winter, the outside sensor is cold, and the duct sensor is hot. In summer, just the opposite occurs. This leaves the in-car sensor to cast the deciding vote. And the in-car sensor is the most effective one anyway. Also, the in-car sensor is mounted so that sunshine coming in the windshield will warm it just as it does the passengers. When the sun goes under a cloud, the in-car sensor immediately forecasts that it's going to get cooler and makes the correction in advance. Looking back at the air inlet assembly, the air inlet door is opened by a two-stage vacuum diaphragm and is closed by a spring. When closed, the air inlet door shuts off the time delay switch, which acts as a master switch on the blower and on the nearby compressor switch as well. When vacuum is applied only to the purple hose, the air inlet door moves just far enough to turn on the time delay switch and let in 20% outside air, along with the 80% inside air that's recirculated for maximum cooling. This vacuum and the vacuum in the tan hose that operates the mode door are controlled by the vacuum valve on the power servo. Whenever the system is regulating or in heater mode, the power servo vacuum valve also sends vacuum through the green hose to open the air inlet door all the way, letting in 100% outside air. We'll take a look at some other vacuum control units as soon as the operator turns the record. Another unit controlled by the power servo is the idle speed-up unit on the carburetor. In the maximum cooling condition, the power servo connects it to the parking brake vacuum supply, which is turned off in neutral and park, so the speed-up unit will raise engine idle to 900 RPM. When regulating or heating, the servo releases the speed-up by sending it a steady vacuum through the blue hose. Also, in the maximum cooling condition, vacuum applied through the red hose shifts the suction throttling valve from its normal 33 pounds to a colder 30-pound setting. The same vacuum, through another branch of the red hose, shuts off the water control valve, so hot water cannot flow through the heater core while the system is operating for maximum cooling. On the end of the water control valve, the thermal vacuum valve provides the time delay for which the time delay switch is named. For in cold weather, it shuts off the vacuum at the purple hose to keep the air inlet door and blower shut off until the engine coolant has warmed up to 120 degrees. Putting these 6 vacuum control units together on one picture with all their hoses may look a bit complicated at first. Fortunately, however, not all the hoses are used at once. We can look at them one at a time, as we have already done for the black hose that carries manifold vacuum to the transducer for the power servo. There are 2 other branches of the black hose circuits leading to the control panel and to the neutral switch for the parking brake. At the control panel, the vacuum supply comes through the yellow hose. When the power servo is set for maximum cooling, this vacuum is connected to the purple hose to open the air inlet door to recirculate. Also to the orange hose to actuate the mode diaphragm, and to the red hose to shut off the heater and reset the suction throttling valve. In addition, the parking brake hose supplies the idle speed up with vacuum in drive, low, and reverse only. In maximum heating, the servo valve seals off the yellow hose, so the system must wait until the thermal vacuum valve opens to pick up vacuum in the purple hose. At the servo valve, this vacuum is connected to the green hose to open the air inlet door all the way. Also, the idle speed-up unit is kept released by a steady vacuum from the purple hose. When the power servo is regulating, the vacuum circuits are exactly the same as for maximum heating, except that the mode diaphragm may be actuated to change over to air conditioning, while still taking in 100% outside air. When the control panel lever is moved to either of the defrost positions, only 2 vacuum circuits are changed. The control panel valve now supplies vacuum directly into the purple hose to avoid the time delay action, and the control panel valve blocks off any vacuum in the orange hose to prevent it from reaching the mode diaphragm. One other difference is that an extra air door, not shown, diverts the airflow to the defroster ducts. In discussing the power servo so far, we have mentioned the mechanical link to the temperature door and the rotary vacuum valve. A third major function of the power servo is the blower speed switch, which controls the blower speed automatically. When the power servo is regulating in a center position, battery current has to go through 4 coiled wire resistors connected in series between the blower speed switch and the blower. This provides low speed. The servo is shown here moving toward the center position after starting out in maximum cooling, which provided a direct connection to the blower for high speed. For each step that the servo moves, one of the resistors is added in, slowing down the blower. This provides 5 blower speeds in all, counting high, 3 intermediate speeds, and low. For each of the direct connections on the cooling side, there is a corresponding one on the heating side. Whether the servo starts from full cooling or full heating, it starts the blower in high and works down through 3 intermediate speeds to low. Now, let's look at the other portions of the blower circuit. The power supply comes through the ignition switch and fuse, then through the time delay switch, the only on-off control in the circuit. Normally, current has to flow through a fixed resistor before going through the speed switch on the power servo. The control panel incorporates a sliding switch, which is not in the circuit, in either off or first automatic position. When the sliding lever is moved to second automatic position, the sliding switch now connects the first 2 terminals. Current bypasses the fixed resistor, then goes back through the speed switch. In this position, each of the 5 blower speeds has been moved 1 step faster. When the lever is moved to first defrost position, the sliding switch connects the second and third contacts, bypassing the speed switch. Now battery current goes through the fixed resistor only, causing the blower to run in medium speed. In second defrost position, the sliding switch picks up an alternate source of battery voltage, bypassing both the fixed resistor and the speed switch to run the blower at maximum speed. When a customer asks our advice on operating his comfort control, we would normally suggest the first automatic position. If several people are smoking in the car, or if one of the vent windows is open, it may be preferable to put the lever under the red mark in second automatic position to take advantage of the higher blower speeds provided. Both defrost positions are special purpose settings for use in unusual weather conditions. In first defrost, the blower runs at medium speed, and the fully dehumidified discharge air is equally divided between the defroster ducts and the heater ducts. This position might be used during a heavy snowstorm, for example. Second defrost sends fully heated air at high blower speed against the windshield for melting ice. Owners may also ask about aiming the air conditioner outlets. Most people prefer to spread the cool air upward and outward, since this also does the best job of cooling the back seat. The left and right outlets should therefore be aimed at a 45-degree angle outward toward the top of each front door. The center outlet should be aimed upward, so the airstream passes a little ways under the rearview mirror, or closed off when there is a passenger in the middle of the front seat. These outlet settings, by the way, are also recommended for service tests on the air conditioner system. When it comes to service testing the power servo, it would be helpful to imagine a large pointer attached to the pivot arm so we could measure its angular travel. There is no service method for doing this, but we can, however, tell what it's doing by listening to the changes in blower speed. The entire program of 7 power servo functions is shown in relation to blower speed in this chart. Actually, these 7 functions are handled by 4 vacuum hoses and 1 mechanical link. To force the system through its complete program, listen carefully to blower speed changes while turning the temperature dial from full cooling to full heating. Coming back from full heating toward full cooling, the sequence is different, because a little over travel has been designed into each of the vacuum valve functions to avoid switching back and forth too easily. These 2 charts are reproduced in your service summary booklets, as are most of the other circuit diagrams, so you can keep them for future reference. For those who will be servicing comfort control systems, this special tester will be a friend indeed. It's as simple as 1, 2, 3 to hook it up and run through the series of tests. To connect the tester, remove the steering column lower cover, unplug the 3-way connector from the amplifier, and plug the tester into both the harness and the amplifier. Also connect the ground wire and start the engine. This tester incorporates a set of precision resistors that can be substituted for the 3 sensors. To test the sensors, simply snap the switch to sensor position and turn the knob. If the system now works correctly and didn't previously, the problem must be in one of the sensors. Snapping the switch to amplifier position substitutes the amplifier and rheostat in the tester. If the system now responds correctly when the knob is turned, check the rheostat resistance with an ohmmeter to decide which is at fault. To check the power servo, try it with full vacuum. This requires removing the glove box. With the regulated vacuum hose off the servo, the system should go to full cooling. Connect the manifold vacuum hose to the servo, and the system should go to full heating. If it doesn't, the problem is in the servo. To test the transducer, a vacuum gauge is used along with the special tester. Basically, this test involves checking the vacuum output of the transducer at 3 calibrated sensor voltages. The special tester can be used to calibrate the temperature dial in the control panel using the substitute sensors and the meter on the tester. The operational test method of calibrating the temperature dial may be helpful in case an owner has his own thermometer mounted on the dash. If the owner's thermometer doesn't agree, the error may be due to its placement. The temperature dial can easily be recalibrated using a ratchet-type tool to hold the hub of the rheostat while slipping the clutch on the dial. To expedite other service operations, the automatic control system can be taken out of action by simply opening all the car windows to force the system to stay at full heating or full cooling. For air conditioner work, such as the performance test, set the dial at 65 degrees to hold the system in full cooling position. This same setup will also permit checking the suction throttling valve adjustment. For tune-up or setting engine idle, we again want to make sure the system is in maximum cooling, so we set the dial to 65 degrees. Pull the hose off the parking brake and connect the vacuum gauge to the hose, so the brake will stay on in drive and the idle speed-up will be released. To check the fluid level on either transmission, you can use the temperature dial to control the engine speed. First, dial 65 degrees to run the engine at 900 RPM for the required minute and a half. Then turn the dial to 85 degrees to get slow idle for checking the level. One recently revised comfort control adjustment involves the time delay switch, which must turn on the blower in recirculate position and turn it off when the door closes. This adjustment is easy to check with an extra length of hose connected in place of the purple hose. A recent production change routed the idle speed-up hose through a revised 7-port vacuum valve on the control panel, providing an alternate vacuum source to keep the idle speed-up unit released at all times with the system off, as covered in the December service man. One more look at this vacuum circuit diagram will show the difference between early cars and late cars. Formerly, the blue hose originated at the power servo valve, but now a white hose carries vacuum from there over to the control panel valve. From there, the blue hose runs to the idle speed-up unit. Another refinement recently made in production involves the in-car sensor. The late-type sensor, identified by a dot of white paint, uses smaller diameter wires made of steel rather than copper to better insulate the sensor from the instrument panel cover. This change is covered in the January service man. But early or late, the ingenious design of Cadillac's Comfort Control and its ability to forecast temperature changes and correct them before they occur are unique in the industry. This is the first fully automatic heater air conditioner capable of holding the car interior temperature steady within a degree from winter to summer without touching the dial. The pre-selected program that operates the system to best advantage lets the driver set the dial and forget it, keeps the passengers comfortable and the owner happy. Cadillac Comfort Control not only forecasts the weather inside the car, but does something about it. Truly a most useful weather forecast.